Yeah, so do keep in mind this may be put on YouTube. So if you don't want to show your face, just keep your camera off and you can type in the Zoom chat when I ask questions. So today we'll talk about weighted AM-GM. So also, just in general, it's best to whisper your answers in the Zoom chat to me since there are a lot of people in class and it's overwhelming if everyone talks out loud. So just like, normal school class might run. Okay, so last time, we proved the AM-GM inequality, which said that, let's say for 3 variables, their average or their arithmetic mean is at least as big as their geometric mean, which is basically instead of adding, you multiply, instead of dividing, you take it to the 1, over n power. So, and this is for non-negative variables. And equality occurs when all of them are equal. So this is the equality case. So in general, it's the arithmetic mean bigger than or equal to geometric mean. So today we'll just extend this a little bit and talk about weighted AM-GM. So weighted AM-GM. So I think I sent out an email with some of the handouts that we might look at for today. But if you don't want to check your email, that's fine. We can just look at these kind of one at a time together. So here it says the sum of x and y is 10. And I want to max x cubed y squared. So unfortunately, it doesn't say max xy, or else we could use the AM-GM inequality directly like we did last time. So how could we maybe deal with the unequal exponents? Anyone have any thoughts? And again, feel free to whisper directly to me in the Zoom chat. So this is a pretty tough question. So it's probably not super fair that I'm just asking it directly. I should probably explain it and give an example. So by the way, everyone can hear me all right, right? Okay, great. So maybe use powers of x. Okay, well, so here's the trick. So, last time, we could use AM-GM on any number of variables, right? Yeah. So I see some suggestions in chat that are pretty good. So, if I could, let's say have let's say I have a different problem. So let's say I have 3x plus 2y equals 10, and I want to max, x cubed y squared. So here I have some coefficients. Does this suggest anything on how I might use AM-GM a bit more creatively to find the max value of x cubed y squared? So yeah, so here, instead of doing AM-GM directly and saying that this is greater than whatever their product is, yeah. So I see some suggestions in chat which says, we can write the 3x, we can break it up into x, x, and x, and the 2y as y and y. And now we can use 5 variable AM-GM on these 5 terms, and it will be greater than the 5th root of, whatever, this thing. So then we can find the max value of x cubed y squared. And this is a problem for xy positive, let's say. So yeah, so if we do this, we can be like, oh, hey, so what does this say? So this says 10 over 5 is greater than or equal to the 5th root of what we want. So we take both sides to the 5th power and we get 32 is greater than or equal to what we want. So now let's see, can we achieve equality, right? So can both sides be equal? So, as a reminder from last time, or to check if you remember, when does equality occur here in this, inequality? So, equality case. Yeah. So, oh yeah. So it'd be good if you whispered to me. But yeah, it's like some people are saying in chat. It's when all 5 variables are equal, right? So when we apply 5 variable AM-GM, so we need x equals whatever equals y. So yeah, so that would be when 3x is 6 and 2y is 4. So when they're all equal, they're 3x plus 2y is 10. So each of the variables is 2. So yeah, equality can be achieved. We just let both variables be 2. So okay. So so what does that suggest we should do with the original problem then? So let me just paste the original again. So it's basically, it looks almost identical, but we don't have coefficients of 3 and 2. Can we do the same thing? Yeah. So I see Vincent says we can use 1/3 x. So yeah, we can split the x into 3, equal things. So let's say we have like x over 3, and x over 3, right? And then the y, we can split it in half. So now on the top, this equals, well, x plus y, which is 10. And we'll just divide it by 5 and say that's greater than or equal to the 5th root of whatever their product is. So yeah, so now we can just, solve for x cubed y squared, and what's the max value of that? So this says 2 greater than or equal to x cubed y squared over 108 to the 1/5. So, we just, this will be 32 times 108, whatever that is greater than or equal to x cubed y squared. So yeah, can we achieve equality? When does equality occur here, if it does at all? Whatever it is, yeah. Yeah, so we need all 5 of the terms yeah, like someone is saying in chat, we need all 5 of the terms to be equal, right? And that can happen. It's when all of these are equal. So basically x over 3 equals y over 2. So yeah. So let's see. So their sum is 10 and we need x over 3 equals y over 2. So let's see, is each, so that's 6 and that's 4, I guess. So this is 6 and this is 4. So I guess x equals 6, y equals 4. So yeah, that would make all 5 of these equal, and we can achieve equality then, since all 5 variables are equal. And I guess we could plug it in and check. So this is 6 cubed times 4 squared, and yeah, that's true. Yeah, it's equal. Okay. So, this highlights that, anytime you have some sort of thing like this, and you have like x to the a, y to the b, if I want to max this, and I'm given their sum or something like that, and I'm told that, they have to be positive or non-negative, then I can do it with some sort of weighted AM-GM argument. So, what would be wrong? So you might be wondering, what if I instead split it like x over 4, x over 2, and x over 4? Right? Why wouldn't that work? Because that would give a different answer. And maybe this is y over 2, or maybe 2/3 y and 1/3 y. Maybe that gives a different answer. But why does that give a different answer, supposedly? So yeah, right. So someone says, and I'm just gonna say someone sometimes, since I don't know if you want to reveal who you are, when you're answering to me privately. So this would still give a true statement, right? We still get a true inequality. It's just that the equality case can't be reached. So if I do 5 variable AM-GM on this, oh, here's someone else. So if I do 5 variable AM-GM on this will be something to the 1/5 power, like x cubed over 32 times y 2y squared over 9 to the 1/5 power. And it's a true statement, but you can't actually reach the equality case. So true inequality, but no equality case, because unless x is 0, you won't ever have x over 4 equals x over 2. False, unless x equals 0. So no equality case. So you can't actually achieve the equality case of this inequality. So yeah, so that's why there's basically only one way to actually break them up, at least for a problem like this. So let me know if you have any questions. We'll just look at a few more examples. And this is important to understand, since some of the future things we'll talk about today will depend on understanding this. Okay, so for number 2, if you have any ideas, feel free to. So how about this time? You can say it to everyone, or you can say it to me. So it'll be more class discussion instead of me checking for understanding. So how might we do this one? So it doesn't quite look like the previous problem. In the previous problem, we had to weight one of the variables 3 times instead of once, and we had to weight the other variable y twice instead of once. And I just kind of made this up, so hopefully I didn't make a mistake in the problem statement. Oh, wait, hang on. Is this good? Yeah, I guess this should be fine. So Kyan says divide by x cubed. That's fine. I guess since x is positive, that's a valid thing to do. So we could divide by x cubed. And then David says, yeah, we can split the x and the x. Like this can be x. So what I prefer to think of it as is that, yeah, so I mean, this is one way to look at it, x cubed plus x cubed. And then we can divide both sides by 3. And then this is basically AM-GM. Yeah. So, we'll have, yeah. So by AM-GM, this plus this over 3 is greater than or equal to this times this times this to the 1/3, which is x to the 4th. Yeah. Okay. So, you can even use it on just when there's one variable. Yeah. So this one's a similar one. Oh, well, we should check the equality case for the previous problem. So the equality case is when all 3 variables are equal. So we need x cubed equals x to the 6th. And these are real numbers. So x cubed is 1. So x should be 1. The other 2 roots of unity do not work since we're just dealing with real numbers. Okay, so that's the equality case. Quality. So, this one is a little bit different. So let's say, and I should have said the way, I prefer to think of it is instead of having, all these, breaking up a variable kind of things, another way you can think of it is with weights. So, here if I divided both sides by 3 up here, we would get x to the 6th over 3 plus 2x. So basically the weights are 1/3 and 2/3. Normally in two variable AM-GM, the weights are all equal. But here, as long as these weights are add up to 1, let's say, it's fine. So, and then this is greater than, basically you weight the 2/3 one twice and the 1/3 one, once, and it's all to the 1/3. Square x to the 6th to the 1/3. Yeah. So these are called the weights, and they generally are non-negative, and they should add to 1. So the sum of the weights equals 1. Okay, so show that for positive x, we have, this is true. So there's probably multiple ways to do this. Yeah, can anyone think of one way? Yeah, so if I didn't say that if I said x was non-negative, we couldn't divide by x, but yeah, I guess we can divide by x cubed, and that'd be fine. So Google says AM-GM to get x to the 9th. I'm not sure if that, can't use AM-GM like directly from the equal weights condition. So, maybe one way we could do it is move everything to one side. This is always something you can do. And then what can we do with this expression? this is a question mark. We're working backwards. Yeah, maybe we can factor. So we can factor out a x squared. Hang on. Maybe, hopefully I made this problem up correctly. So is this always true? Oh, yeah, this is always true. So we'll have two factors of this and an x plus 1, because we can use difference of squares on that. And since x is positive, and this is non-negative. Yeah, so it can't equal 0. So, I guess from this proof, when does equality occur? Let's see.
When x equals 1.
Yeah. Oh, and in case you weren't here earlier, I'm recording the meeting, and yeah, it might be better to just say things in the Zoom chat in a whisper to me, since it may be put on YouTube and not everyone wants to either face reveal or voice reveal. So yeah, so when x equals 1, this will be 0 squared, and this can never be equal to 0 when x is positive. So that's a fine solution. The intended solution was just weighted AM-GM, where basically you'll have, so maybe what we can do is we can say, like, let's say we want to find some constants alpha and beta so that this is greater than this, and maybe some other constants gamma and delta or something, such that this is greater than or equal to this. And we want these two weights to add up to 1 and these two weights to add up to 1. So we can just add. So in the end, we can, we can just add the two inequalities. So the previous problem, suggested that, we can kind of, well, maybe it wasn't. So, if I want this plus this to be greater than or equal to this, maybe one way to do it was we weight this by 2/3 and this by 1/3. So this is true by the weighted AM-GM, and then we can weight this by 2/3 and weight this by 1/3, and this will be true. So if we want to write it the original way, this would be like this. It's the same as the previous problem, and we can do similarly here. So then we just add these two and we're done. So add. Yeah. So I guess in general, yeah. Okay. And both of these have an equality case where x is 1, I believe. Since here we need x to the 6th equals x to the cubed, and here we need x to the 6th equals x cubed. So equality can be achieved. Okay. So let's see. Maybe we should do one where it's backwards. So I'm just gonna make up a problem like this. Let's say we told a product and we want to find the min value of some uneven sum. So the idea is, can I make this the product side of a weighted AM-GM, where the sum side looks something like this? Maybe Maybe this is not possible, but we'll see. Actually, let me see if this even works. So if I try, yeah, maybe it doesn't work out this way. Yeah, I guess this is maybe the best we can do. Hang on, this isn't even, yeah, we're doing this backwards, aren't we? So Vincent says use x cubed over 2, x cubed over 2 and 3y squared over, let's see, does this work? Okay, yeah, this would work, I guess. So I guess the idea is still to break it from this side and it should still work out. Okay, cool. So let's see. Yeah, we want to make the exponents even, so it makes sense to break the 3 into, 3 plus 3 divided, and we want to make it 1 and 1. So we want 2 of these and 3 of these to make the exponents even, yeah. Okay, so x cubed plus y squared, this is broken to like this, like Vincent said. So then y squared plus y squared plus y squared. So this over 5 is greater than equal to xy over some like 4 times 27. And maybe I'll just write it to this. Hang on. So it's the 5th root of that. So this is equal, xy was 1, so this is 1 over 108 to the 1/5. So I guess it's 5 times 1. It's 5 times 1 over 108 to the 1/5. And this is x cubed plus y squared over 5. So let's see, can we achieve equality? So x cubed over 2 equals y squared over 3. So maybe we should write it x cubed is 2/3 of y squared. So this is, their product was x was 1. So let's see, this is 1 over y cubed equals 2/3 y squared. So yeah, there should be some y so that this is true. So yeah, I think equality can be achieved. Equality case. Okay, great. Oh, there's a typo in the handout. Oh, wow. Okay, so all of this can be generalized to something that kind of involves, well, yeah. So you can kind of generalize this to Muirhead's inequality. So maybe I should just open up what I typed. So this is kind of generalizing weighted AM-GM when you have multiple variables. So the intuition is that if I have like x squared y to the first, and let's say x cubed plus y cubed, this should be true intuitively by AM-GM because we can do this, we can weight this twice and get that this is true, and weight y twice to get the other one is true by AM-GM directly on these three terms. And then we just add and we get the result. So, it seems like maybe, we can rewrite these as like x cubed y to the 0 and y cubed x to the 0. So it seems like the sequence 3, 0 is somehow like, when we do this, it's like, I don't know what the symbol is for it. It's probably some different symbol. But it's better than the sequence 2, 1 for the sequence of variables like 2 and 1 here. So by better, I mean like greater than when we write the symmetric inequality. So, and maybe we should see like an example with 3 variables too. So I'm trying to think of what's like an actual good 3 variable case. So let's just try like x to the 7th y cubed z squared. So if we take the symmetric sum over this, is this bigger than the symmetric sum over like, let's say x to the 6th y to the 5th z? Oh, I think I made this up so that it doesn't work that well. So yeah, sure. Let's change this to 4 and 2. So this just means you do it over all permutations of x, y, and z. So there's 6 terms here. So, for instance, this would be and then, yeah, all permutations of x, y, z, you permute them all 6 ways and put the corresponding exponents on them. So there should be 6 terms in each side. I don't like this. This is not good because what did I do here? So 7, 7, 5, 3, and 6, 7, 5, 2, 6, 4, 4. Maybe this is okay. Yeah. So maybe we should try an explicit example with weighted AM-GM for, yeah, something like this. So we need to somehow weight these in the correct way. And this may not be super easy. Let's see. Yeah, so maybe as a homework exercise, try to find the weighted AM-GM that shows this. I'll find the weighted AM-GM to show this. Okay, but yeah, if we take a look at the Muirhead's inequality, that's just, oh, so there's a question, what do I mean by the 6 permutations? So if you have something like this, like a cubed b squared c to the first, if you do a symmetric sum over it, this just means, so A, C, B, B, A, C, B, C, A, C, A, B, C, B, A, and you take them to the same powers, 3, 2, 1, 2, 1, 3, 2, 1. So in the language of group theory, you're applying the symmetric group to the ordered set A, B, C on 3 variables. So that's what that means. The other notation that's really common is cyclic sum. So this would mean if you had cyclic sum, this just means like you cycle through. So B cubed C squared A plus C cubed A squared B. So here you cycle through like a necklace. Here you do all symmetries. So you have to be really careful when you do this, because let's say you have the symmetric sum on 4 variables, right? Let's say you have like A to the 6, B squared, C squared, D squared, and you do the symmetric sum. Well, here you would basically get, all things of the form like this, but there's 4 of them, right? Or I guess there's 6 of them. You would get six of these plus 6 of these, because you do it over all 24 or 4 factorial permutations. So you have to be careful that, the symmetric sum notation, you mean what you mean, what it's supposed to mean. This is like the standard definition of symmetric sum. Because, all permutations of B, C, and D that leave A fixed will give a term like this. So there's actually 6 terms that look like the thing that I'm gonna box in green. So you have to be a bit careful on what it means sometimes. I guess in this case, you could just do symmetric cyclic sum and that would be fine. But it doesn't always work out, the way you want it to work out sometimes. Because sometimes it's like somewhere in between where if you have A to the 6th, B to the 4th, C squared, D squared, neither this nor this will give you, coefficients of 1 on everything. Because with the cyclic sum, you're missing some terms. Like, it's always 6, 4, 2, 2 in that order. And then you just cycle through the variables. Whereas with the symmetric sum, you'll have a coefficient of 2 factorial on each term. Because you can swap the D and C terms and get a different terms, but they look the same because their exponents are the same. Does Vieta sum come in this form in some way? Like, is it expressible in this notation? Yeah, I mean, so. So, if we have 4 variables, that's a good question, So, you have the sum of the terms taken 3 at a time, which is this thing. So this would be a cyclic sum, I suppose. And then you have the sum of the terms taken 2 at a time, which would be so this one is neither symmetric nor cyclic, I guess. So, you do all 4 choose 2 ways of here. But, you can weight it. So this would be, I just call, when I do it, when I write it, I just indicate this, but it's neither a cyclic sum nor a symmetric sum. Because if we did cyclic sum on like x something j, like x1, this would have 4 terms. And the other one would have 24 terms. Because it'd be like this to the first, this to the first, this to the 0th, and this to the 0th. So this would have, it'd basically be like 4 times that, 4 times. x1, x2 plus dot 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 x3, x4. Yeah. So Vietas, it's not really cyclic because the cyclic sum, it would be just, you would be missing the x1, x3, and x2, x4 terms. So you only have these 4 terms. So maybe a better way, a handout for Muirhead is you can just, you can either look it up on Wikipedia, or you can look at like, let me see if I still have the tab open. Yeah, so this is a good article with a lot of the inequalities. So if you want to go here, the 12th one is Muirhead's, and it explains it properly. I mean, it says it properly. It may not explain the intuition for it, but there's probably better ways to say it. Let's see. Yeah. Another way, so if we go back to Muirhead's, so basically, like in some of my examples, like let's say this is 3, 0, right? In this example. So the sequence is 3, 0 is somehow like greater than 2, 1 when you do the kind of cyclic sum over it or symmetric sum over that. So you would say that 3, 0 majorizes. I forget what the symbol is, but maybe it's like this, majorizes 2, 1. And I think it's pronounced majorizes or majorization. So here you would just see, oh, 3 is bigger than 2. 3 plus 0 is bigger than or equal to 2 plus 1. And the last one has to be an equality. So like the sum of these exponents should be the same on both sides for this to apply. And this is generalizing the weighted AM-GM arguments. So, what this says basically is that when you do the symmetric sum over the AI sequence, it's greater than or equal to the symmetric sum over the BI sequence. So for instance, like, let me see if I can make up an actually good one. So let's say 9, 6, 3, maybe better than 8. I want to make one with all distinct numbers, but it's kind of hard to do so. So maybe 8, 4, 2, and maybe this is majorizes 7, 6, 5 or something. So basically, this would say that the symmetric sum of A to the 9, B, C, symmetric greater than or equal to symmetric sum A to the 8th, B to the 6th, C to the 4th, and so on. And there should be some weighted AM-GM argument for it. So apparently in Olympiads, at least a long time ago, it's better to just write the weighted AM-GM inequality instead of citing Muirhead's. Like it's like better stylistically, but I think it should be fine just to cite it. So maybe let's just copy this over. So, and this would be a good exercise for me too, because I didn't do this beforehand. But let's see if we can actually find 10, 5, 2, 9. Yeah, that works. What would be the smallest one with 6 distinct numbers? So So the majorizes, just so it's clear, it's like the first term is bigger than or equal to the first term. The sum of the first two terms is bigger than or equal to the sum of the first two terms in the second sequence. The sum of the first three terms is bigger than or equal to the sum of the first three terms in the second sequence, and so on. All the way until the last one, where you have but the last one is an equality sign. So the sum of all the AIs is equal to the sum of all the BIs as I goes from 1 to n. So, maybe we'll just stick with the 3 variable case, and then this should be an equality sign. But if you have more variables, only the last one is an equality, and all the rest before are weak inequalities. So, yeah, that's what it means for a sequence to majorize another sequence. And then with that concept in mind, you can express Muirhead's inequality as a theorem with this notation. And it turns out, the AIs, they don't have to be rational or integers. They can be like, irrational too. But then you need something over the reals to prove it, and not just like a finite number of weighted AM-GMs. So maybe another way you can express it is like, let's say we have like a cubed b to the 0 greater plus a to the 0 b cubed is greater than or equal to this one, like we saw before. Maybe another way to write it is that the smaller one, it can be it's basically some like doubly stochastic matrix. So let's say 1/3, 2/3, 2/3, 1/3 times like something like this, a cubed b cubed. So by doubly stochastic, it just means the sum of each column is 1 and the sum of each row is 1 in the matrix that is square right here. So maybe we can write it as, so if I multiply this matrix out, one sec, this is blocking my, if I multiply this out, this will be, so instead of writing that, we should just do it on the sequence of exponents itself. So, if the sequences are, if the bigger one can be, if the small one can be, I guess, kind of composed of the bigger one times a matrix like this, then we're good. So let's see if this is actually, so I guess this would be 1, 2. So this would be 1 plus 0 and 2 plus 0. So 1, 2. So if you have some square matrix where all the rows add up to 1 and all the columns add up to 1, then let's call that matrix like P. Then, and I write the bigger sequence here. Let's call it vector B and the smaller sequence here. Then B is set to majorize A as if you list all the components of the vectors in order. So that should be in equal signs, I guess. So A, B majorizes A as a sequence. So that's how Wikipedia defines it, but it turns out to be equivalent to the thing I said earlier about what majorizes means. So this is doubly stochastic. So apparently, stochastic just means like it can be a, well, I'll just define it and not say where it's useful, but sum of each row is 1. Sum of each column is 1. Or is like, yeah, that's fine. And it's a square matrix. So, but I prefer to think of it in terms of the sequences thing. where you have this sequence of inequalities. So yeah, so this is true by Muirheads because 1052 majorizes 863 according to this definition of majorization. And there should be some weighted AM-GM that proves it. I just probably need to think more clearly on how to find that. So you can try to find it on your own, and it'd be a good exercise too. So yeah, because 10, 5, 2 majorizes 8, 6, 3. Okay, so maybe we should look at some example problems. Let's see. Okay, so this seems reasonable. For a lot of Olympiads where they're just integers, you can just say think of Muirheads as a generalization or like formalizing when weighted AM-GM can work. But just like so it says in Thomas Mildorf, who I guess was pretty good at inequalities, in his handout that it's a named theorem, but if you want to write Olympiad solution, you should just you can just read this. You should check if Muirhead's criterion works and find the weighted AM-GM and show that in your solution instead. How simple this is questionable, but it's doable. So yeah, I guess let's look at number 2. So number 2 is kind of annoying because it's not homogeneous. So homogeneous just means that each term has the same degree as a multivariable like polynomial term. So here everything is degree 1. Here everything is degree 2. We'd like to homogenize it so that everything is like the same degree. And we can do it because we're given this condition, and we can also apply AM-GM since they're positive reals. So AM-GM needs homogeneous. So let's multiply the left side by 1, and we'll multiply it in the way like this is a 1/3, so that now it becomes the degree 2 polynomial. So now all the terms look like a to the 4/3, b to the 1/3, c to the 1/3. So the cyclic sum of that, I guess. I'm just going to write it out since. So 1/3, 4/3, 1/3, 1/3, 1/3, 4/3. I think. Okay, and this is greater than or equal to, I mean, it's the other way actually. So yeah, so now, what's an appropriate weighted AM-GM for this? Let's see. So here, these are like a squared, b to the 0, c to the 0. So because this majorizes 4/3, 1/3, 1/3, we should be able to find some weighted AM-GM solution. So there's a question, do you just add up the exponents and that becomes the denominator for the weights? That's a good question. And how do you find the weight? Yeah, that's a good question. So my thought is that, these add up to 2. So, but I'm going to write it as 6/3 because they're in thirds, right? And, maybe it's even more clear if you make the substitution like, a equals x cubed, b equals y cubed, and z equals, or whatever, like c equals z cubed. And then it would say 600 majorizes 411 or something. So, but I'll just do it for this case. So this is 6/3. So maybe we want to break it into 6 parts. So if let's say the a squared is broken into 6, then I want it to be in the proportions 411. So we need some constants here, like alpha 1, beta 1, gamma 1. So I'm thinking maybe this is a good way. Oops. 1 and 1, 411. And this is over 6. So we have yeah, so this works. Sorry, I need to think quietly because I'm not good at talking and thinking at the same time. So then we would just add up all 3 of these. Yeah, so this works. And then there's the third one. So c squared over 6 is greater than, well, you can compute it. So a, b, c to the, so yeah, I guess this would be a good example where not all of the coefficients are repeat. There's none of the terms here are equal to any of the terms there. So anytime you have a condition like this, it allows you to homogenize, which means makes all the terms the same degree. So this is called degree 2 because the sum of the exponents is 2. Homogenize is the word or the verb. So it just takes a bit of practice, but you can figure out the weights. I guess the way to figure out the weights from, yeah, maybe we should look at another example of how to figure out the weights, and then we can come back to this special case of how to figure out the weights when it's like a to the k plus b to the k plus c to the k. So, we've been going for an hour. Let me just put up one more problem and then we can take a 5-minute break. Where is it? Oh, I closed it. Well, yeah, so, if you want to take a short break, we'll resume at 8:06 Central Time. I need to get some water and probably rest from talking a bit. Okay, so we can resume. Let's see. Hope everyone's summer's going well. Okay, so ABCD is 17, and we need to minimize this 9 variable expression. So what's annoying about this expression? Why can't we just apply AM-GM directly to this? So Drita says one of them has squares and others is products. Well, yeah. Well, so there's so we have different powers. Well, that's also true. So, if I wanted to, the product things, they can be some sort of symmetric sum, right? Like if I just multiply it out, oops, AC, AD, BC, BD, CD. This is a symmetric sum. What about the squares? Give me 1 sec. I'm going to change chairs. What's annoying about the sum of the squares? You have a 4 variable, expression. Yeah, there's no d squared term. This is Cayenne. Right. So if there was a d squared term, this would be easy, right? If there was a d squared term, we could just, so no d squared term. Frowny face, sad face. So, if there was a d squared term, we could just apply AM-GM directly on 10 variables. And the result would just, on the right, would have like A, B, C, D all to the same power, right? So, okay, it doesn't work to just apply 10 variable AM-GM because there's no D squared term. So how can we deal with this, I guess? So there's a question, would it be a good idea to change the D from the products to 17 over ABC? Yeah, that might be a bit ugly. Let's see. So that doesn't actually change whether or not we can apply AM-GM directly or not, I don't think. I mean, we can try it and see. It doesn't hurt to try it and see. But basically we have like, the AB, AC, BC term, and then we have a D times the other 3 terms. And if we plugged in 17 over ABC for this, we would just have something like 17 like 1 over BC plus 1 over. So, we like the fact that it's homogeneous. I want everything to be degree 2 if possible. If I use this substitution, it's no longer homogeneous, and that's not as good. So that's a good thought, but we want to keep it homogeneous. So maybe that's not the best idea if what we're trying to do is apply AM-GM in some way. So what we basically need is we need to maybe put some constant k, right? so that maybe this, and then some constant j in front of all of these, in front of some of these. So, we can just put that inside the k. I'll just write sum AB so that when we apply AM-GM on it, it'll be like ABCD to some power over 3k plus 6. So, let's take a tally, right? So we need more d terms because we're missing a d squared, right? So far, we have this. We have an a squared. We have an AB, AC, and AD. And that's, wait, is that it? Yeah, that's it, right? For the a squared terms. So there's an a to the fifth in our product. And then there's a b squared term. There's, a b, bc, bd, and ba. Those are all the terms with the b in them, and there's b to the fifth of them. But for d's, right? So this is, if we keep a tally of the d's, there's no d squared term, so x on that. But there's a dA, dB, and dC, right? So there's d cubed of them. So we want to weight them in such a way, and the c is the same as the b and the a. So c squared. So we want to weight it in a way so that we have more d's, right? So there's only 3 terms with a d in them. If I can increase the weight of this, let's say okay, so let's not call this k because this is a bad idea because we don't get any extra d's in them. Let's call this k. Now we can get extra powers of k if we do this for each term with a d in it, right? So if we did that, so this would become d to the 3k, right? And then each of these terms with the d in them, instead of it being c to the fifth, it'd be c to the 4 plus k, right? Because we have 2, 1, 1, and then k. So we need these two to be equal because we need an equal number of A, B, C's, and D's. Yeah. So let's see, what happens here. So we equate these and we get that k is, well, so k is 2. 2k is 4, k is 2. So yeah, so that's how we can find the weights. And this should work in general. You'll have some linear system of equations. So what we just found is that with our expression, we have getting distracted by other thoughts. So instead of having BD, we have BD, we weight it twice. And instead of having DA, we weight it twice. And then the same for CD, we weight it twice. So now, if we apply AM-GM on these 12 terms, it'll be correct. So this divided by 12 is greater than or equal to, so let's double check, right? How many A's do we have? We have an A, and A, and A, right? So that's A to the 6th. B's and C's are kind of be the same thing because it's symmetric in A, B, and C. Now D's, we have 6 D's, right? So D to the 6th. And then this is over 2 to the 6th. And then, we have some 12 through sign. So yeah, so that's how we find the weight in this particular problem. So what this says is that, what did it say again? So this is A, B, C, D square rooted over oh, this is 2 to the 6th. So this is over 2, square root 2. And ABCD was 17, I guess. So this is like something like this. What did the problem say again? ABCD is 17, yeah. So our thing is just we multiply both sides by 12 and we get 12 root 17 over 2. Is like the, I guess, minimum value of that expression. And then you can compute the answer from there for this particular competition, but we don't need to worry about that for now. So let's check that equality can be achieved, right? So we need all 12 terms to be equal. Is that even achievable? So A equals A squared, B squared, and C squared equals AB equals AC equals BC equals BD over 2 equals AD over 2, and so on. So there's a question, is it common that you can find the weights from a linear equation? So it might be like more complicated than this. You might need 2 variables and 2 equations, or 3 variables and 3 equations, but they'll all be linear equations. So let's look at another example after we finish checking the equality case here. So this basically says, since we're non-negative, that A equals B equals C. So let's just call all of A, B, and C A. So we need, so this is A squared equals A squared equals A squared equals AD over 2. So we can cancel out an A and we get A equals D over 2. Yeah, that's fine. So this is the equality case, and we just need to scale this so that, their product is 17. So that's doable. Like, A, B, C, D over 2. If we increase each variable by the same factor, eventually it will equal 17. Right? This is solvable if we make this condition and this condition for A, B, C, D. So equality is achievable. So, maybe let's look at the previous example where we had x cubed plus y cubed greater than x squared y plus y xy squared. So we need to solve the system of equations. Let's see. Yeah. So, there could be, so let's say it's like alpha x cubed plus beta y cubed greater than x to the c, y to the d, and c plus d is 3. So I guess the way you do it is, yeah, so maybe we should assume alpha plus beta is 1. That's fine to assume, to scale it like that. And then y to the beta, 3 beta 3. So we don't need the square root if this is actually equal to 1. Yeah, so I guess alpha and beta should be in the ratio of c to d. So here we have like the coefficients of x cubed and y cubed, alpha to beta, are in the same ratio as c to d, because c has this role and 3 beta has the role of d. So this equals like, so in this case, it'd be 2 to 1, right? 2 to 1 in this case. And also alpha plus beta equals 1. So this is a system of equations, and it's just into thirds, right? One of them is 1/3, the other one is 2/3. So this is alpha, this is beta. So I guess this would be the system of equations for this particular like AM-GM weighted. If we have to do something more complicated, it's very similar, I think. Like maybe we have x to the 5th y squared, symmetric sum over 3 variables, right? I think it would be very similar. So let's just change the numbers so that they're small, x squared y. So we have so maybe this is greater than or equal to, the one we had similar to something we had earlier. Let's say 4/3. Let's make it 5/3, 2/3, 2/3. So I think these are degree 3 things. So we make a symmetric sum out of this. So this is supposedly greater than or equal to x to the 5/3, y to the 2/3. So there's 2 of these because we can swap the x, the y, and the z, and then 2 of these, and so on. I should use the thin pen. So let's see if we can come up with the system of equations. So there's some way to weight these 6 variables so that it's bigger than, like, let's say one of these. This is a bit ugly. But I imagine the idea is just, you just call the weights A1, A2, A1, A2, A3. And maybe some of these are actually equal because x squared y plus A2 x squared z plus A3 y squared x and A4 y squared z and so on, so that it's bigger than exactly one of these terms, like x to the 5/3, y to the 2/3, z to the 2/3. And I think this would be easier if we just did some substitution and said like x is x1 cubed. So instead you have all integers if you prefer. So sum of this over 3 variables greater than sum of this over 3 variables. And there should be a way to solve the system of like linear equations to make it work out. So I think that my guess is like all these 2 terms will have the same coefficients. So let's just say a x1 6 y1 cubed. And I think this is, it's probably good that I'm trying to do this on the spot since I don't usually do this. So b, let's change to y 6 x plus c. And then this is bigger than, let's say the term x to the 5th y squared z squared. So we just need, so let's see. Well, we need the sum of the weights A, B, and C to be 1. We need to have more x's than y's and z's. So probably B will equal C since the number of y's and z's is the same. And then A is different than the number of A is bigger. So should it just be 5 halves as big? Let's see. So so let's calculate the number of x's. And then this will be x1 cubed. So from this term, there will be this number. And from this term, there will be this number. Sorry, this is really messy. So this is like separated from that. So I should just, oh, I'm at the bottom of my PDF. That's fine. So let's just copy this over. So we'll have x1 to the 6a plus 6a plus 3b plus 3c. And this should be x to the 5th. So we have this equals 5. And then if we use the same variables and keep track of the y's, then every term with a y, let's see, we'll have y1 to the 3. And then this is to the a. And then there's also the same thing, y1 to the 6 to the b, y1 to the c, 3 to the c is, so this should be y squared. So yeah, you get some system and you get a plus b plus c equals 1. Why isn't it 2a plus b plus c equals 1? Oh, you might be right. Hang on, let's see. So let's see what are the weights. Yeah, you're right. So I put a as the like a is the same weight for these two terms and those two terms. So yeah, this should be 1/2. It should be 2a plus 2b plus 2c equals 1. Because there's actually 6 terms that I just assume that these two coefficients are equal, A3 and A4 are equal, and A5 and A6 are equal. And sorry, I didn't finish writing out the terms, but you can imagine what they are. This is like Z. So yeah, thanks for the catch. So yeah, you get some system of equations and it's solvable and it's linear, so it should be good. So you can always find the weights if you can solve linear equations. Yeah, and it should be doable from here. Okay, let's see. So let me know if there are questions on this, because I think I tend to write sloppy and say some things possibly incorrectly if I try to write and talk at the same time. Okay, so I think this is why were we able to assume that those two had the same weight? Uh, so I assumed that these two had the same weight because on the right-hand side, we had like x to the 5 over 3, y to the 2 over 3, z to the 2 over 3. So it's a good question. I don't know if it's actually correct to assume that. But because these have the same exponents here, it makes sense that yeah. Yeah, maybe it doesn't make that much sense. Yeah, let's see. It makes sense that these have the same weights. So it makes sense that these two, let's see. Yeah, I think it should make sense. Because the exponent of y and z were the same, that means we can swap anytime you have two expressions where if I swap y and z, it's like the two terms just swap with each other, then their coefficients can be made the same. Because it's like if I apply the symmetric group. So if you know group theory, which it's obviously not a prereq for this, but basically if I have some permutation of x, y, and z, and y, z in parentheses represents swapping the y with the z, then I can apply it to the other side in two. So if I swap the y with the z, these two terms swap with each other. Hang on. So maybe now that I think about it, that's a really good question. So there's also this. So there's a y squared x, y squared z plus z squared x, z squared y. So if I swap y and z, let's see, which two? So these two should have the same coefficients. I think I had that backwards. So these two should have the same coefficients. Like this is A4 and A6. Let's put it so it's in a different color. So if this has coefficient A6 and A4, then A4 equals A6. I think I had that wrong on the previous page. And then if I swap x and y here, then they should have the same coefficient. Yeah, so A3 equals A5. This is A3 and this is A5 as the coefficient. So yeah, sorry, that's a really good question. Thanks for pointing that out since I had made a mistake in the previous page. So it should be that like the y squared becomes a z squared, y squared x becomes a z squared x. So it should actually be that these two coefficients are the same because swapping the y with the z should give like the same weight because the end weight of 2/3 and 2/3 are the same. And then these two have the same weight because that's what happens when you swap the y with the z. Yeah, thanks for the good question. And feel free to point out if I make mistakes because that's very possible. So this is all I had planned for today. If you guys have any other random questions you want to ask, you can feel free to do so. Yeah, so feel free to ask me anything. I'm happy to answer. It doesn't have to be related to what we talked about, but if you have to go, that's fine. Or if you don't have any questions, have a good week. Hopefully, we'll be back next Wednesday. I'm gonna stop the recording, so you can feel free to ask anything.